Hi guys. So in this next video, we're going to talk about artificial transmutation, which is different from natural transmutation. So let's circle this word here. Whoops, I don't have my pen on. Artificial means that it is not spontaneous. It's almost something that's forced. It's a reaction that needs help getting going, okay? And you kind of know that it's an artificial transmutation just by looking at it because it's going to have two reactants. That thing is not going to do something on its own. It needs a second thing in order to react with to get it going. Okay, so fission is my first type of artificial transmutation. And to help you remember the definition of fission, I want to write this here: fission, division. Okay, so fission division. What fission is when you have a heavy nuclei and it splits or it divides into lighter nuclei. And aside from splitting apart into smaller things, it's so important that you know we also produce a ton of energy. So when you guys see a fission reaction written out, it's going to be very common for you to see plus energy on the right side to show that a huge amount of energy is being released. Okay. Typically, guys, your reactant particle, your heavy particle is uranium. It has a mass of 235, very heavy. Polonium is also a common element to see in the front there. But see how I have this second reactant, this neutron? So what's going to happen is this uranium atom is not going to split by itself. It needs to be bombarded. It needs to be hit by that little neutron to give it help splitting apart. So those are your two reactants. That's how you know this is forced and this is not happening spontaneously. Okay. And what happens is that a little bit of mass is actually converted into energy. We're getting a tremendous amount of energy here. Okay. So that's a fission reaction. Fission reactions they have a couple different uses. One is in a nuclear power plant. So this is just a diagram showing you how we make electricity from a fission reaction. So this kind of looks a little complicated, but we have these fuel rods. So guys, the fuel is the uranium. The uranium has a tremendous amount of nuclear energy stored within its nucleus, the uranium atoms. So they undergo a fission reaction, right? Now, if we just let this fission reaction go, I want you to notice that at the end of the reaction, not only are we making two smaller atoms, but we're producing a bunch of neutrons. So what happens is those neutrons that we make, they're going and they're hitting other uranium atoms to cause more fission reactions. If we just let all of those neutrons go and hit more uranium atoms, our fission reactions would be out of control. That's more like what's going on inside of a nuclear bomb. In a power plant, we need something to control the reaction, and these are the control rods. So they absorb some of the neutrons that are created. So not every neutron is hitting a uranium atom and a reaction is just going to get out of control and too hot. Okay. Then we have these turbines that are taking this heat that's being made and turning it into electricity. And that electricity is going to travel to our homes. Okay, so it's pretty cool how that works. These are just some graphs that you guys can, you can obviously pause and look at, but it's just showing graphs of where in the United States, what kind of fuels we're using to get energy. So here's nuclear. That was in 2009 versus in 2016. So our nuclear usage has stayed about the same. It does look like our natural gas consumption has increased and our coal has decreased over the years, which is a good thing. And then here is a look at Japan, okay, and how they've changed from 2009 to this is their plan for 2030. So it's just interesting to see what other countries are doing. Another chart that you guys are free to take your time and look at. Okay. Pros and cons to fission reactors. So I feel like as far as like nuclear energy goes, that's like a, you know, people agree with it and people disagree with it, and there's definitely reasons for both sides. So a pro for using nuclear fission for electricity and having nuclear power in the United States, a pro is that no carbon dioxide is produced. So as far as like comparing nuclear energy to fossil fuels, I guess we can say it's cleaner. You know, that we worry about the amount of CO2 produced because of climate change. So if we can find energy that doesn't make carbon dioxide, that's a good thing. Another pro is that fission is very efficient as far as the amount of energy goes. It's a lot. So we're getting a lot of energy as a product, which is a good thing. Another good thing, guys, if we're using nuclear energy, we're not relying on other countries for oil. So if we have more independence, that's a good thing. Okay. Cons. So I just got finished saying that nuclear power fission reactions are clean. If there is an accident, if there is a meltdown, I want you guys to look back up at the products of that fission reaction that we talked about before. So, aside from making lots of energy, we're making these super, like, they're lighter than uranium, but they're still pretty heavy elements. And we talked about how the heavier the isotopes are, the more likely they are to be radioactive. So, along with energy, we're getting this radioactive waste that, if the reaction is controlled, we can collect this waste and we can store it appropriately. If there's an accident and a nuclear power plant melts down, all of this radioactive waste is just coming out. And there have been disasters in history that we're going to talk about later, and how bad that radiation exposure is for the people living and the animals living in that area. Waste disposal is also a con. We're eventually going to run out of room. These radioactive products that we're putting away, they're definitely decaying over time, which is good. But we could definitely run out of room for where we can put that waste. So that's not good. The reactant, uranium, is not readily available. Like as far as like finding uranium, that's not something that we come by, super easily. So that's something to think about as well. Okay, fusion. Fusion would be a game changer for us. So fusion is the opposite of fission. It's when you take two light nuclei and you combine them to make a heavier one. And just like with fission, we get a huge amount of energy. Okay, so this definition is more vague than you guys need to know. Think about the lightest element on the periodic table. What is it? It's hydrogen. Your two reactants are always some form of hydrogen. I'm going to use hydrogen with a atomic mass of 2. Hydrogen can weigh 1, 2, or 3. So any combination of hydrogens on this left side are okay. What do I get when I add 1 plus 1? I get 2. My product is always helium. It could have a different mass depending on the masses of the 2 hydrogens you started with, but this is going to be our regular helium plus energy. Okay, so what are the pros of fusion? We actually get more energy than we do in a fission reaction, which is kind of crazy. Um, the good thing is that there's no radioactive waste. Aside from energy, we're making helium. And there's actually a helium shortage happening in the world, so that would probably even benefit us in another way. Another good thing, guys, the reactants, hydrogen, are readily available. It's very easy for me to get hydrogen um, compared to me needing uranium to start a reaction. So you're probably thinking like, okay, well, if fusion is better in all of these ways, why don't we just use it? Think about what you're trying to do, guys. You're trying to take a positive nucleus and smush it together with another positive nucleus. Do two positive things want to combine? Absolutely not. Think about trying to put together two positive sides of a magnet. Once they get close, they're going to really repel each other. It's going to be hard for you to push them together. It's the same thing with fusion. Right now, as it's going right now, it takes more energy to push the two atoms together than we're going to get out of the reaction. So, because our positive nuclei repel. So right now, it's not worth it until we figure that out. Right now, the only place that has enough energy for fusion to occur naturally is the sun. It's hot enough to get those particles together. Okay, so that's pretty cool. Key to recognizing artificial transmutations. So fusion is another artificial transmutation, just like fission. And look, we have two reactants. Anytime you see two things on the left side of that arrow, you know that it's something that had to be forced. It didn't happen automatically. Okay. Now, I put off talking about the hydrogen bomb, the nuclear bomb. This is another application, I guess, for a fission reaction. But a hydrogen bomb is basically three bombs in one. This trigger right here, once it hits a chemical explosive area, we detonate this chemical reaction, which is going to create enough heat to start my uranium or my polonium. In here is where your fission is going to occur. Once your fission reaction is occurring, it's making enough energy to actually also detonate or start a fusion reaction. Okay, and if you just look at some of these pictures, guys, they're very very scary. But if you think of the amount of energy that a nuclear reaction can produce compared to a chemical one, I want you to compare a nuclear bomb to a firework. Which one creates more energy? Nuclear, big time. So nuclear reaction, more energy than a chemical reaction. On the reagents, they'll ask you guys if you can compare the energy released from a fission reaction to like a combustion reaction. It's a ridiculous amount more. Okay, so that's something to look at. Particle accelerators are exactly what they sound like. These are machines that are going to speed up particles. So this is our way, guys, of studying particles when a nucleus is broken down. So these particles need to be sped up, and they're sped up using magnetic and electric fields. We know that if something has a negative or a positive charge, it's going to be attracted to something else. So we use that attraction to make these particles move in a certain way. These particles are going to hit a nucleus, okay? And once that bombardment happens, we can study what comes out of that nucleus. We can study the pieces and the energy released, okay? So this is just a picture of the Hadron Collider over in France and Switzerland. You can see this is the pathway of the particle. So you can see how big it is, right? How much speed you're going to have to build up to break that nucleus. And this is where the Higgs boson was discovered. This is physics that I don't even understand, but it explains why matter has mass. People are amazing. And this is a picture, an overview of the particle accelerator that's here on Long Island. So it's pretty cool that people studying this stuff. All right, so that is it for today, guys, with artificial transmutation. Our next video will talk about what we use, other uses for radioactivity. Okay, have a great day.